All right, guys, this video is going to cover section 4.6, which is on linearization. So I want you to take a minute and I want you to look at these three graphs. And the question is, what do they have in common? Okay. So at first, kids, look at this left graph and ask yourself, what kind of graph is this? So some of you might say it's linear. It follows the format of y equals mx plus b. Okay. And what do you think this next graph is? Some people might say it looks like y equals sine of x. Okay, now how about this third one? And you might look at this third one and be like, I don't know what the equation of that is, but I'll tell you that it is a 13th degree polynomial. Not that you would ever deduce that on your own. But what they have in common is that they are all actually the same. And what I did here is I took this 13th degree polynomial here on the right and I zoomed in. If you zoom in really closely on this little section, that's the linear piece that you're seeing in the left graph. And then if I zoom out a little bit, that's what you're seeing in the middle graph. And the idea is that if I zoom in close enough on any graph, eventually that little section that I zoomed in on will look linear or appear linear. Okay? So local linearization, if you break down the word, okay, locally or looking nearby, we are going to use a linear function. Right? This is one way to approximate a function's value. And sometimes when we do problems like this, kids are like, I don't understand why I have to use this process. Well, a lot of times they not created, but they use this methods back in the day when calculators weren't a big thing. Okay, so a lot of this stuff is meant to be done without a calculator. So local linearization, like I said, local, we're going to look nearby, and linear. When you think of something linear, okay, hopefully tangent line comes to mind. Tangent lines are always linear. They follow that format of y equals mx plus b, or if you're using point slope form now, so the y minus y sub 0 equals m times the quantity x minus x sub 0. Okay? So the tangent line of a function f of x at x equals a can give you an approximate value of f of x for points close to a. Okay, we don't want to go far away from a. Okay, so that's the whole local idea. Like for example, if I want to do an approximation on this graph near 0, I don't want to come over here towards 1 or 2 and go too far away from that point. And I'll show more of that here in a minute. Okay, so another idea that goes along with this is we can look at the concavity. So that's a new vocab word for us. We haven't talked about concavity yet, but it looks at the curvature of a graph. Okay, so if something is concave up, this portion right here is concave up like a cup. Okay, and then concave down is like a frown. This portion right here is concave down. And we're going to do a lot more with this in the days and weeks to come. But that's just a brief intro to concave up versus concave down. If a graph is concave up, our approximation with our tangent line will always be what? And I want you to think about this. So if I make this my point A, okay? And I create a tangent line there. So it's going to look something like that-ish. Rough sketch, clearly. Okay, I can go locally or nearby to approximate other points. So for example, if I put point B here, I could use my tangent line to approximate the value of B. I could come over here and I could do, I don't know, Z. I could use that to approximate the value of our function at Z. But if I go too far away from it, like say I come over here to, I don't know, F. Right? This is going to not be as good of approximation. The further away, that you get from that initial point A that we use to create the tangent line, the worse your approximation is going to be. Okay? But let's go back to this concavity idea. So if the graph is concave up, our approximation is always going to be what? An over or underestimate? Estimate, my God, I can't speak. And hopefully you look at this and you see that the entire time the graph is concave up, the tangent line is below it, so it will always be an underestimate. Similarly, if I go to a portion that's concave down, I don't know, let's go over here, and I'm going to call this point C. Okay, if I draw in my tangent line there, okay, I can use that to find points or estimate points nearby, so like D. Okay. Now here, my approximation with my tangent lines will always be an overestimate. And you can see that the tangent line is always above the function. So all of your estimates will be above the actual value in the real function. Okay? Now, to write the equation of these tangent lines, and I'm going to use A here. To write an equation of a tangent line, we need a point and we need a slope. So our point would be A comma f of A, and our slope would just be f prime of A. So if we fill that into our point slope equation, we're going to have y minus the y value, which is the f of A, equals m, which is the f prime of A, and then x minus the x value. Okay, so we're going to use the point that we care about and the slope at that point to write the equation of the tangent line. And then we'll use that tangent line to approximate nearby values. So some key points. Continuous functions will begin to look straight if we zoom in enough. Okay. On a small interval, these functions will appear linear. And like I said, that's why we use the word local linearity, because we're looking nearby for the approximation. You don't want to go super far away because then it won't be a good approximation. And we're using the linear tangent line to do that approximation. And then the third one, it is simple, generally simple, to find the output of these linear functions. And like I said before, they came up with this a long time ago when we didn't really have calculators to evaluate some of these crazier functions. And at the end of the day, calculators are really just using an algorithm, because the calculators are using addition, subtraction, multiplication, and division, and they're using an algorithm to do all of these harder, crazier things that we want them to do. So they basically create an algorithm to find different values. All right, let's look at some examples. So example 1, f is concave up on its domain, and f of 4 equals 5, f prime of 4 equals 3. So for A, it says, what is the estimate for f of 3.8 using the local linear approximation? You see that wording right there? Automatically, you should think, okay, I need a tangent line. Okay, so at x equals 4. So to write an equation of a tangent line, this is part A, we need a point and a slope. Did they give us that? Yeah, they gave us the point. This is the point 4 comma 5. This is the x, this is the y. And they gave us our slope, f prime of 4 is 3. Okay, so to write the equation of our tangent line, we'll do y minus 5, which is the y value we care about, equals m, which is 3, and then x minus 4, that's the x value that we care about. So that's the equation of our tangent line. Now we want to use that to approximate f of 3.8. Well, 3.8 is an x value, so we're going to plug that in for the x. And I claim this can be done by hand. Okay, the idea is a lot of times these local linear approximations will be non-calculator questions. So 3.8 minus 4 is negative 0.2. 3 times negative 0.2 is negative 0.6. And then if you add that 5 over, you have 5 minus 0.6, which is just 4.4. Okay. Part B then says, is it an under or overestimate? So they told us that the graph is concave up. And I'm not saying we don't know what the original function is, so we don't know exactly what this graph looks like. But if it's concave up, it has generally this shape to it. And we had said before, the tangent line will be underneath it if you draw in a tangent line at the point that you care about. So if this is the point, 4, 5. Okay. And we tested nearby at 3.8. And we got out 4.4. That's the y value of the estimate. Okay, that's not the actual value on the function. That's our estimate. Okay, you can see that it would be an underestimate, and it asks us to explain. And that's because f of x is concave up on our interval. Okay? All right, let's go to example 2. Consider the differential equation. And we haven't talked about differential equations yet. That's going to be coming in chapter 7. But this is a differential equation, this derivative. Okay, differential equations are just your derivatives, basically. And it says, let y equal f of x be the particular solution to that differential equation with the initial condition 2, 0. Once again, we don't know a lot of this terminology yet, but the particular solution, we're talking about our antiderivative, which is our integral, which also we still haven't seen, but that is coming in January. Okay. We can still do this problem though. Part A says, write an equation for the line tangent to the graph at the point 2, 0. So to write an equation of a tangent line, we know we need a point and a slope. Well, they gave us the point 2, 0, and they gave us the derivative. So we can find our slope using the derivative. So if we evaluate the derivative at the point 2, 0. So we have e to the 0, and then let's plug in 2 for the x. So we get 4, 8, minus 10, negative 2, e to the 0 is 1, so we just get negative 2. So the differential is just the derivative at the end of the day. We can use that to find our slope. So the equation of our tangent line would be y minus 0 equals negative 2, and then x minus 2. Okay, so that's part A. Then part B wants us to use the tangent line to approximate 2.2. All right, so let's plug in 2.2 for x. Once again, you should probably be able to do this by hand. So 2.2 minus 2 is 0.2, and negative 2 times 0.2 is negative 0.4. Cool? All right, our last example here. Approximate the square root of 122 using a local linear approximation. Once again, you see that wording right away. The idea of a tangent line should be coming into your head. Now, this problem gives us a lot less information than the others. So you kind of have to think through, what am I going to be using here? And the whole idea here to write an equation of a tangent line is you need a point and a slope. So ideally, we need a point that we know or that we can easily find. So a value that we know that's close to the square root of 122, hopefully you're saying, well, I know the square root of 121 is 11, not 1, 11. So that would give us a point. If I put in 121, I got out 11, so that's an xy. Well, so then we have a point that's near that we could use, but we need a slope. And if you're thinking about slope, hopefully you're thinking, well, what's a function I could use? Well, what function are we really using? What function are we plugging these values into? Hopefully you're saying the square root of x, right? I just plugged in 122 for x. Here I just plugged in 121 for x. Okay, well, let's derive that. And if we rewrite that, we get 1 over 2 root x. Okay, so now I can evaluate that. I'm going to turn this into dy dx instead of, not that it matters, y prime, but I'm going to evaluate that at the point that we picked before. So the 121.11. So if I put that in, hopefully you can see. I don't know what's happening. There we go. 1 over 22. So to write the equation of our tangent line, we would write y minus 11 equals 1 over 22, x minus 121. Then we can use that, so that's the equation of our tangent line, to approximate the square root of 122. So the 122 will just be the x value that we're plugging in here. So y minus 11 equals 1 over 22, and then 122 minus 121. Well, that's just 1. So I really get, if I add the 11 over, 11 plus 1 over 22. And you can leave that alone. If we don't have a calculator, leave it like that. And the key thing I want you to notice is if I would put in my calculator, that's approximate, 11 plus 1 over 22, I get 11.045 repeating. If I put in the calculator the square root of 122, I get 11.04536. So our approximation's good to 3 decimal places. That's pretty good for not using a calculator at all. We're down to the thousandth place. That's awesome, which some people might find cool. Some people might be like, you're a nerd. But write down any questions or thoughts you have. I have a 15-minute time limit, so I'm out of time. We can talk more about this tomorrow.